Hello there. Um, Hope y'all are having a good day again. I'm quickly just going to go over the practice problems and the section 13.2 review that I gave y'all. Try and go quickly, just so you can understand it, but then I want to give you time to do your study guide in class, because I just found out your games are this weekend. Okay, so I want to try and give you as much time in class as you can to do your study guide. Okay, so Miss Smith, like I said, I think I said yesterday, is also going to be giving you credit for these problems that you did. So don't think that you're just doing them to stay busy. You're getting points for them. Okay, I would never just do something like that and not give you credit for it. All right, so let's quickly go through these then. All right, so number 8, this is on page 319, if you forgot where we were. Okay, so number 8 says, a piece of aluminum house siding is 3.6 meters long on a cold wintry day of negative 28 degrees Celsius. How much longer is it on a very hot summer day at 39 degrees Celsius? Okay, so we're going to be using the linear expansion, but we're trying to see how much longer it is going to be. So we're going to need to find the change in length, okay? So how much longer will it be? That'll be the change in length. Okay, so we'll use our equation. Change in length equals the coefficient of linear expansion, the little alpha thing, times the initial length times the change in temperature, okay? This one's pretty straightforward. You're given the coefficients on the other page, so I hope that you could recognize that, the one for aluminum. Okay, so with that, you have the change in L is going to be equal to 25 times 10 to the negative 6 degrees Celsius to the negative 1st. All right. So that is your coefficient there, that alpha right there. And then you've got your initial length, which is 3.66 meters, times your change in temperature, which is going to be 67 degrees. All right, and when you work that out, you should get 6.1 times 10 to the negative 3rd meters, or if you wanted to put it in millimeters, that is 6.1 millimeters, okay, these are pretty straightforward. I actually really like these problems because they aren't very confusing at all. All right, I'll just let you take a look at that for a second. The 67 down there is the change in temperature, okay? Try and hold it still. All right. Like I said, that is pretty straightforward. Number 9 is very similar, but instead of looking at or trying to find the change, we're trying to see the final length of it. So that'll be our L2. So we'll have to remember that. Okay. So number 9 says a piece of steel is 11.5 meters long at 22 degrees Celsius. It is heated to 1221 degrees Celsius, close to its melting temperature. It'll say how long is it. Okay, so that we aren't looking about how much it grows, so we aren't looking for the change. We're looking at how long it is finally at the end. Okay, so therefore, instead of looking for the change in L, we're going to be looking for our L2. So to get our L2, we have L2 minus L1, that's our change in L, right, is equal to your coefficient times your initial length times the change in temperature, T2 minus T1. All right, so to get that L2 by itself, all you have to do is add L1 to both sides. Plus L1 plus L1. All right, I'll show it to you in just a second. Let me write it all out. Equals L1 plus. All right, so this is the equation we're going to use. So all I did is I broke up that change in length. So I made it L2 minus L1, and then I just added L1 to both sides to get L2 by itself, okay? And now all we do is plug in. All right, so we have our initial length is 11.5 plus our coefficient is 12 times 10 to the negative 6 degrees Celsius to the negative first times our initial length again, which is 11.5, times our change in temperature, so it'll be 1221 minus 22. Remember, you just subtract that first before you can do your multiplication. And when you do that, you should get 12 meters. All right, so that's just simple plugging in there. You get your coefficient again from that other chart. So like I said, you'll either have the chart for your test, or if you have one that has that you need the coefficient, I'll just be like, and the coefficient for aluminum is this, da, 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 da. So you won't have to worry about knowing that, okay? Off the top of your head, at least. All right. The last two deal with the coefficient of volume expansion, so they're kind of cool too. But it's just like these, really. You just needed to know that is with the volume expansion. All right, so number 10 says an aluminum soft drink can with a capacity of 354 milliliters is filled to the brim with water and put in a refrigerator set at 4.4 degrees Celsius. The can of water is later taken from the refrigerator and allowed to reach the temperature outside, which is 34.5 degrees Celsius. What will be the volume of the liquid? Okay, so to find the volume, we have, if you look over on page 318, you saw, it would be 2 days ago now that we looked at the coefficient of volume expansion, which is beta, right there. And you have the change in volume equals the coefficient of volume expansion times the volume times the change in temperature. It's right above the example problem right there. So that's all we need to do, or that's the equation that we need to use to find the answer to this problem, okay? So we have the coefficient of the volume expansion also on that chart as well. All right, so the change in volume is going to be change in V equals coefficient times volume times change in temperature. All right, so let's plug in there. We've got 210 times 10 to the negative 6 degrees Celsius to the negative first is our coefficient. Our volume is 354 milliliters. We found that from our problem there. And our change in temperature is going to be 30.1. All right, and that'll give us 2.2 milliliters. Okay, but the problem doesn't ask for the change. It asks what will be the volume of the liquid, okay? So the change is 2.2 milliliters. So to get what the final volume will be, we'll have to add the initial to the change. So our initial volume was 354 milliliters, right? Plus 2.2 milliliters is the change. All right, and that will give us 356 roughly. Really 356.2, but nearest whole number is fine. All right. So it's basically the same thing you did for the other one. Okay, great. That's part A. Part B, you do the same thing, but you do it with the aluminum as the coefficient. So all you have to do, I'm not going to erase all of it because it's the same thing. You just have to change the coefficient and change it to the coefficient for aluminum, which is 75 times 10 to the negative 6th. So that's all you do there. And then you still have the 354 milliliters and the 30.1 degrees Celsius is the difference. All right, and that comes out to be 0.8 milliliters. All right, and it's asking the volume again. That was just the change. Okay, so you do 354 milliliters plus 0.8. And that should give you 355, roughly. So it's the exact same thing, you just change your coefficient to aluminum because the can is made of aluminum. Okay, great. All right, in part C, how much liquid will spill. So all that really is the difference in volumes. We'll show the amount that spills. The difference of the change in volume will show you how much will spill. So, that was to tell me to do this lecture for you all. I have to babysit in an hour, so I'm trying to get this done. Okay, so part C says how much liquid will spill. So that is the difference in the change of volumes of the can and of the water that we just had, okay? So all you do is do 2.2 milliliters minus 0.8 milliliters. And when you find the difference there, it's 1.4 milliliters. So that's how much will spill. So very simple. All right. Now, let's look at number 11 quickly. All right, number 11 says, a tank truck takes on a load of 45,725 liters of gasoline in Houston at 32 degrees Celsius. The coefficient of volume expansion, B, or beta, for gasoline is 950 times 10 to the negative 6 degrees Celsius to the negative first. The truck delivers its load in Omaha, where the temperature is negative 18 degrees Celsius. How many liters of gasoline does the truck deliver? Okay. So we need to find V2 for this. So it's the same way we kind of did the change in length for this. So we have our V2 is going to be equal to V1, because remember the change in volume is V2 minus V1. So you just move that V1 over because you add it to both sides to get rid of it on the V2 side to get it by itself, plus the coefficient times the initial volume times the change in temperature. All right, so now we just plug in. We're given 45,725 plus, they give us the coefficient, 950 times 10 to the negative 6 times the initial volume. I'm running out of room over here. So it'll be times the initial volume again, which is 45,725 times the change in temperature, so negative 18 minus 32. That should give us 43,553 liters. Okay, so you see, I'll let you write it down real quick, then I'll talk. Okay, so you see that they start off with 45,000, almost 46,000, and they end up with 43,500, right? So it asks, part B says, what happened to the gasoline? Well, look at the temperature. It goes from a really hot temperature of 32 degrees Celsius, which is, about 90 maybe. Yeah, about 90 degrees, and then it goes to negative 18, which is really cold. So the change in temperature causes the decrease in the gasoline, actually. So that's what happens to it. That is part B. All right. So I hope you found those pretty easy. I thought they were pretty straightforward, nothing really tricky there. All right. And let's quickly, it's already been 18 minutes. Okay. So let's quickly go over 13.2 in the section review, and then I'll let you work on your study guide. I'm so sorry if you got to. Well, you have the weekend. It'll be fine. Okay, so 2.1 says, starting at 0 degrees Celsius, how will the density of water change if it's heated to 4 degrees Celsius and then to 8 degrees Celsius? So remember, water is most dense at 4 degrees Celsius, so that'll help. Okay, so the density will increase as the temperature increases from 0 to 4 degrees Celsius, because water is most dense at 4 degrees Celsius. But above 4 degrees Celsius, the density will decrease when the temperature increases. That again makes sense. It has like this point where it's the most at 4. So below, like anything below 4, it's going to be not as much, and it'll increase, the density will increase there, and then it'll go down again if it is most dense at 4 degrees Celsius. Okay? All right. So 2.2 says, you're installing a new aluminum screen door on a hot day. The door frame is concrete. You want the door to fit well on a cold winter day. Should you make the door fit tightly in the frame or leave extra room? Okay, this is on a hot day, okay? So both are going to shrink in the winter. So aluminum and the concrete. But because of the coefficient of aluminum and concrete, the aluminum will shrink more than the concrete. So to keep the door fitting well in the winter, we should make it fit really, really tightly in the summer, because it'll shrink even more, right? Okay. Hopefully that makes sense. All right. 2.3. Why could candle wax be considered a solid? Why might it also be a viscous liquid? Candle acts like a solid. It will not change shape under applied forces, provided they do not act on it for a long time. So if it's not a significant amount of time that the force is there, it will not act on it, okay? If forces are applied for lengths of time, the wax tends to flow like a viscous liquid, okay? So if there's a long amount of time, then it will start to flow like a liquid. The forces will cause it to have like a liquid sense to it, okay? And then the last one, if you heat an iron ring with a small gap in it, as in figure 13-21, will the gap become wider or narrower? All right, so it's going to become wider, but think about it. Okay, so think about it as if the gap were still filled with metal. All of it were filled with metal. The particular wedge of metal would expand along with the rest of the ring, right? So the gap would also then expand or become wider as you heat it. So that's the whole thing with linear expansion, right? When you heat something, it's going to get longer, okay? And so the gap will get longer as well because it's not connected. All right, well, that is all I have for you today besides your study guide. You're going to get it right now. Yes, and you'll have time to do it over the weekend, so good luck with that. And yeah, I will talk to y'all soon and find out about your games. Good luck.